Today's lesson is going to focus on types of transformations that we haven't really investigated yet. And those are transformations that are involving changing the x value, or horizontal stretches and compressions, as well as horizontal reflections. Of course, we've seen reflections before, reflections over the x-axis, and that always affected the y values. So flipping a parabola from opening upwards to opening downwards. But when we talk about horizontal reflections, or reflections over the x-axis, it's like taking anything that was in the positive side of the x-axis and then flipping it to the negative side of the x-axis. So a reflection over the y-axis. So for this unit, we've looked at the transformations of vertical stretches and compressions. We've seen reflections over the x-axis. We've talked about translations left and right, and we've talked about translations up and down. So how we're going to start this is we're going to investigate our radical function here, f at x equals the square root of x. And I'm going to make a table of values for x. And the table will include values for x of 0, 1, 4, 9, and 16. And I'm going to draw a sketch. Essentially, this is our parent function, and just with a couple added extra points. So my x values will go here in my table. My y values, or I'll call them my f at x values, will go here in the table. And I'm going to have the numbers 0, 1, 4, 9, and 16. Now, why did I choose these numbers? Well, because these are perfect squares, so they're going to be really easy to graph if my function is equal to the square root of x, just like this. And so when x is 0, square root of 0 is just 0. When x is 1, square root is 1. When x is 4, square root is 2, and so on, all the way down. And I'll graph these on here. I'll make each block here worth 2 so that I can fit this with x being 16. So 0, 0 will fall right on my origin spot right there. 1, 1 will come right here. I'll make the y-axis still be equal to 1. When x is 4, y is 2. When x is 9, so 2, 4, 6, 8, 9, y is 3. And when x is 16, so 10, 12, 14, 16, x, or y value is 4. And there's my radical function right here. I'll just put on a little scale here to help you see this. There we go. And I'll draw a nice smooth curve through these points. There we go. So this is my f at x function, which is the square root of x. So now I'm going to create a table, but I'm going to create a table for this function, g at x, which is the square root of 2x. We haven't really seen any functions where we have a number out in front of the x itself. We always had a number out in front of, the whole brackets, or not actually relating to the x. But now we're going to see what happens when I put a 2 in front of that x. So here I have g at x. This is going to be the square root of 2x. And so for my x values, I'm going to use some slightly different numbers. So 0, half, or 0.5, 2, 4.5, and 8. And so to get my y values, or my g at x values, I just take whatever number x is, multiply it by 2, and then take the square root. So 0 times 2 is still 0, and the square root of 0 is 0. That didn't change. Half times 2 is 1. The square root of 1 is 1. 2 times 2 is 4. The square root of 4 is 2. And we'll see that all of these, 4.5 times 2 is 9. Square root of 9 is 3. And 8 times 2 is 16. Square root of 16 is 4. I get whole numbers. So let's plot these. So 0, 0 goes here. That didn't change. Half goes up to 1, so that's right around there. 2 goes up to 2. Mistake here. My half right there was slightly off. Okay, so on half I go up to 1, so that's right around here. 2 over I go up to 2. 4.5 over I go up to 3. And 8 over I go up to 4. And so if I draw a nice smooth curves through these ones, let's see what happens here. I have a function that sort of looks like that. This is my g of x. So what actually happened here? Well, I want to point out some points here. Let's look at when y is equal to 3 right here. So my points when y equals 3, I have 1 right here, and I have 1 right here. This is at 4.5, and this is at 9 right here. And I guess 4.5 will be even closer to right around here. And how we see this here is, this was the original point. My new point is exactly half the distance to the y-axis as the original point was. This was 9 over. My new point is 4.5 over. And we see the same thing for some other values of y here. Here my y value is 4 on my original function, but now on my new function my y value is 2. So it's half the distance. And even over here, this was at 16, and my new function, my x value, is at 8. Half the distance. So what does this mean for what happened, or what type of transformation this was? Well, what happened was my original function was horizontally compressed into half the size that it was before. Everything got squished half over. So if I did have a point even at 1, well, 1 turned into half. The only point that didn't move was the point 0, mainly because half of 0 is still 0. We have a special name for points that don't get moved on a transformation, and we call those points invariant points. So invariant points are points that do not move after a transformation. So what kind of rule can we see here? Well, let's think back to when we were talking about translations left and right. Remember inside the brackets with x, if we saw a bracket, and just for example, we had x plus 4 in the brackets. We remember that it's backwards thinking inside the brackets, and because it's plus 4, our brains need to think that it's minus 4, and we're actually moving left 4. The same sort of rule applies when we have numbers in front of x. So when we see this 2x here, we immediately need to suspect that it's either a stretch or compression, but it's backwards or opposite to what we might think it is. So if the number's out in front, like this a value, we know that's a vertical stretch. If it was a 2, it would be a vertical stretch of 2. But when a 2 is inside with the x, it's actually opposite. So it's not a vertical stretch, or sorry, a horizontal stretch of 2. It's a horizontal compression of 1/2. It's like saying it's the reciprocal of whatever number is in front of x. So if there was a 3 in front of x, it would be like saying a horizontal compression of 1/3. If it was a 10 in front of the x, it would be a horizontal compression of 1/10. So this leads us to an interesting question then. What happens, or what type of transformation do you think will happen if we put 1/4 in front of the x? So I have a square root function as my parent function, and I have 1/4 out in front of it. What do you think the transformation will be? Well, the same rule applies. We still take the reciprocal of whatever number is in front of the x. So the reciprocal of 1/4 is simply 4, which means we're going to have a horizontal, and because the number 4 is greater than 1, we're going to have a horizontal stretch of 4. Like I said, it's always backwards thinking to what you think. Anything with dealing with the x's. It's just how it turns out. So now we've added this extra k value, we're going to call it, in front of our x term in the transformations. So we have the plus minus out front, which deals with the vertical reflections, or reflections over the x-axis. We have our a value that's there, which deals with the vertical stretches or compressions. When a is greater than 1, it's a stretch. When a is less than 1, it's a compression. Our d value here is still determining if we go left or right. The c value here is determining if we go up or down. And now our new plus or minus k, we've added to this transformed notation. So the plus minus, we haven't talked about yet. This k value, if the k value is greater than 1, well, we saw that when k was 2, this was actually a compression. So when k is greater than 1, we have a compression, or a horizontal compression. So we have a horizontal compression. And we say it's a horizontal compression of the reciprocal of k, or whatever 1 over k is. So if k is 2, it's a horizontal compression of 1 over 2, or 1/2. When k is less than 1, but greater than 0, so still positive, we notice, like up here, that it's actually a stretch, or a horizontal stretch, and again, of the reciprocal. So when k is less than 1, but greater than 0, we have a horizontal stretch and again, of whatever the reciprocal of k is, so of 1 over k. This sometimes gets confusing because k in this instance is a fraction, so 1 over a fraction, well, remember you just flip the fraction. So 1 over 1/4 is the same as saying 4 over 1. Well, what happens when k is negative? So for this plus minus here, it's actually a minus. Well, it works the same as the plus minus out in front of this a. If it was negative, we would have a vertical reflection, or reflection over the x-axis. Well, if this k value is negative, we'll have a horizontal reflection, or a reflection over the y-axis. So when k is negative, we're going to have a reflection over the y-axis. And my pen here seems to want to not write properly. So let's see here. Over the y-axis. There we go. Reflection over the y-axis. Okay, one example to end the lesson. So let's see the graph where f of x equals the absolute value of negative x minus 3. I'm going to move back slightly to the last slide here. I'm going to move back to the last slide here. And I just want you to notice that this k value is multiplying not only to the x, but it's also multiplying to the d value. This is the normal way of writing this. So it's like we factored out whatever this k value is outside the x. This x will never have a number directly in front of it. It'll always be factored out. So if there's a d, we factor it outside of the d as well. So for our example right here, we have negative x minus 3 inside the absolute value function. So hopefully you can see right away that our parent function is the absolute value function. So our parent function here is y equals the absolute value of x Now, what has replaced this x is this negative x minus 3. But rule number 1 here is that I need this x to be positive, so anything out in front of this x needs to be factored away. And not only does it need to be factored from the x, but also the d value. So the initial instinct here is that this is going to be shifting to the right 3 units because of backwards thinking. But let's factor out this negative and see what it actually looks like. So when I factor out the negative, I end up with my function at x is equal to the absolute value of negative, and then in brackets, I'm going to factor out that negative, x plus 3. And so you see that we are doing a horizontal reflection or reflection over the y-axis, but our whole graph is actually shifting left 3 units, not right 3 units. So let's write out what these transformations are again. So we have a horizontal reflection, or I'm just going to say a reflection over the y-axis. And the second thing here was a shift left 3. And I don't mind if you just say left 3. I know what you're saying. So we'll create our RST chart to help us graph these transformations. This is going to be a simple RST chart, not too much going on here. So my x value and my y value. There we go. My reflection over the y-axis. So we're going to use a box here that we've never used. Reflecting over the y-axis affects the x values by multiplying them by -1. So I'm going to take all my x values and multiply them by -1. Now, some people were getting confused. They thought this x right here represented the same x up here, but this is just a multiply sign. It doesn't mean a variable x or anything like that. I'm just saying the operation we're doing here is we're multiplying by -1. And then we're moving left 3. Again, left 3 affects the x values, and we're going to take each x value and subtract 3 because we're moving left. So I only fill in those 2 boxes for this example. Because it's the absolute value function, I have memorized the key points for this. So the key points for the absolute value function, I have -2 and 2. I have -1 and 1. I have 0, 0, 1, 1, and 2, 2. Fix this there. Perfect. And I'll map these to their new spots. So when I map them, notice how no changes are being made to the y values, so they'll all stay the same, 2, 1, 0, 1, and 2. And my x values will multiply them by -1 and then subtract 3. So -2 times -1 is +2, but subtract 3 is -1, and the y value stays the same. -1 times -1 is 1, subtract 3 is -2. Y value stays the same. 0 times -1 is -1, and then -3 is -3. 1 times -1 is -1, -3 is -4. And last but not least, I bet you can guess what the point here if you follow the pattern. 2 times -1 is -2, and then subtract 3 is -5. So I'll start by graphing my base function, or my parent function. So that happens at 0, 0, 1, 1, and 2, 2, -1, 1, and -2, 2. And I'm going to kind of cheat here. I'm going to throw some lines on here, some straight lines. I don't have the luxury of using a ruler, so I can do this. This is my parent function here. I used f at x for the new function, so I need to just use, I'll just say y equals my parent function, absolute value of x. And then my new points, so I'll do them in red here. So -1 and 2, -2 and 1, -3 and 0, -4 and 1, and -5 and 2. And I'll draw these points on here, these lines. go. See if I can change the color here. I'll make them red. Makes more sense for these lines, I think. Perfect. Okay, so now what happened here? If you just looked at this, you would say to yourself, I know I see everything shifted to the left 3, but was there a reflection over the y-axis? I know that my RST chart and when I said what the transformations were, there's a negative there. But did it actually reflect? Well, it did actually reflect, but notice how this function right here, uh, if you reflected it over this y-axis, well, this side would fold over to here, this side would fold back, and you'd actually end up with the exact same function. In fact, all of the points, if you just had a reflection over the y-axis, they would all be considered invariant points. None of these points actually moved. But so this one did do the reflection. The reflection had to come before the shift left. So we reflected first, which didn't change anything, and then we shifted everything to the left 3. So that's why we only really see a shift left 3, but the reflection did happen as well. And I will just say that this is my function f of x right here. And I need to properly label some points, so I have the point -3, 0 right here. Let's label -4, 1 and -5, 2. And then in black over here, I'll label these 3 points, so 0, 0. This point here, 1, 1, is the transform point -4, 1, so that's proper for me to label these ones over here because these did get reflected over. And so this one here is 2, 2. And there we have it. Okay, so now it's your turn. You're going to find this handout posted on our class calendar under today's lesson. So today's lesson is on Friday. And I want you to try number 2, number 3, 4 to 7, sections B and C, and number 8. It's going to practice graphing and talking about horizontal stretches, compressions, and horizontal reflections, which are reflections over the y-axis. Okay, so enjoy this homework, and here's another smiley face for you. Put some little eyebrows on there, maybe some tufts of hair, and maybe that'll get you in the mood for doing some horizontal transformations. See you next time.